Section 5.3, we're interested in surface area and volume. Of solid figures. And so here we're mixing and matching a bit with some of our ideas from area. We notice that if we're looking at a box, so if we have a box that has a length, a width, and a height, we know that it's basically made up of 6 rectangles. So we notice that the surface area is the total area on the surface of the figure. Kind of intuitive. And so notice that for this box, we notice that we're going to have the surface area is going to be 2 times length times width, because we have a top and a bottom, plus 2 times width times height, because we have a left side and a right side, except we write it as times. Oops. 2 times width times height, because we have a left side and a right side, plus 2 times length times height, because we have a front and a back. So this is basically top and bottom, left and right, front and back. So if we looked at a box that was 10 centimeters by 12 centimeters by 20 centimeters, we notice that surface area, which is abbreviated as SA, is going to be 2 times 10 times 12 plus 2 times 12 by 20 plus 2 times 10 times 20. And so we get 240 square centimeters plus 480 square centimeters plus 400 square centimeters. And so we get the total surface area is going to be, it's going to be 800, 1,000, 1,120 square centimeters. And that's essentially how much surface area of, say, wrapping paper we need to cover it. Although obviously that would be exact. You need a lot of Scotch tape. So, as long as we're on this shape, we notice that volume of a box is length times width, length times width times height, and just like we had square units for area, we notice we're going to get cubic units for volume. And so we notice that for this particular box, we're going to have 10 times 12 times 20, 10 cm times 12 cm times 20 cm. So we're going to get 200 times 12 is 200, 2400 cubic centimeters. So we notice that going up from a rectangle, we notice that we can also create things that are like rectangles. A prism is made up of two matching plane figures connected by rectangles. So essentially a box is a rectangular prism. So I should say a right prism. A box can be considered a right rectangular prism we notice that we basically have two matching rectangles connected by more rectangles. We can also have a right triangular prism. So a right triangular prism has two triangles connected by rectangular sides. So something like that. And so we notice that the surface area for a prism, surface area for a right prism, is equal to the areas of the top and bottom plus the area of the sides. So in general, we think of that bottom area as the base. So as a formula, we know surface area is going to equal 2 times area of the base, because the area of the top will match the area of the base, plus n times, plus the sum of the areas of the rectangular sides. So sometimes this is easier, sometimes this is harder. So we notice that if we have a triangle, that was 3 by 4 by 6, and we knew that the prism was and now the prism is over here. And where the prism is 5 units tall, we know that surface area. Actually, we can make this a little nicer. If we know it's 3 by 4 by 5, it just so happens that makes it a nicer triangle. And we'll make it 6 units tall. We know the area of the base is going to be 1/2 times 3 times 4. And then we know the area for those sides is going to be 3 times 6 plus 3 plus 5 times 6. Let's use the 4. 3 times 6 plus 4 times 6 plus 5 times 6. So we have those 3 rectangular sides. One of them is 3 by 6, one is 4 by 6, one is 5 by 6. So we end up getting 2 times, that'll be 6, plus 18, plus 24, plus 30. And so we end up getting 12 plus 18 plus 24 plus 30. And so we get 84 square units. And you notice that I will wind up using that term square units and the idea of units squared more or less interchangeably. Those wind up being the same idea. So we notice the volume of a right prism is given by area of the base times the height. And so as for this prism we were just talking about, we notice that the volume is going to end up being that 1/2 times 3 times 4 multiplied by the height of 6. And so we end up getting 6 units times 6 units is 36 units cubed. So, in general, you'll be given all of those side lengths. A little bit different is for a for a pyramid. So, a right square pyramid, we notice that we're looking at a square base and then sides going up to a point. And so notice now, we notice that the base is a square and the other 4 sides are triangles. And so these are actually kind of interesting because we notice that when we're trying to find the surface area, we need to know the slant height. So we need to know the slant height of, basically the height of the triangular side. So the slant height is essentially the height of the triangular face. So we notice that if we were going to say, how are we going to construct it? We notice that the area, I'm going to phrase it, we know that if we've got if we said that the side length was d, so we've got square faces length d, we notice that our area, the surface area, is going to wind up equaling d squared plus 4 times 1/2 times d times L. And so we wind up getting d squared plus 2dl. I think your textbook uses s instead of d for the side lengths, but when you're talking about surface area, using s gets a little bit confusing. So we notice that if we were going to look at a specific example, if we had a pyramid and we knew that the base was 6 meters by 6 meters, and we know the slant height is 5 meters, we know that the surface area is going to equal that 6 meters squared plus 4 times 1/2 times 6 meters times 5 meters. And so we get 6 square meters plus 60 square meters, which winds up giving us 66. Why did I say that? You notice that what we end up actually getting, if we square 6 meters, we get 36 square meters. So you get 36 meters squared, 6 times 6 is 36, plus 60 square meters gives us 96 square meters. So these are actually kind of interesting because once we learn a little bit more trigonometry, we're going to discover that it's really easy to draw a pyramid that's completely impossible. So it turns out that if this particular pyramid exists. So if we make it 6 meters across, a 6 meter by 6 meter square and 5 meters tall, it turns out we also know that, well, actually the side length, the slant height is 5 meters. It turns out this pyramid will turn out to be four meters tall. And if we wanted to, we could actually build that pyramid. We could physically build a pyramid that was 4 meters tall with a square base that was 6 meters by 6 meters and have a slant height of 5 meters. If, on the other hand, so this pyramid could exist. On the other hand, if I just arbitrarily drew a pyramid and said that it had side lengths 5 meters by 5 meters by 2 meters, yeah. If I just arbitrarily could, let's actually do it this way. Let's say 7 meters. So if we tried saying a slant height of 7 meters, we can create a surface area for this. That'll turn out to be 25 square meters plus 1/2 times 4 times 5 meters times 7 meters. We can do the calculations. The trouble is that this pyramid may not be possible to construct. You'd have to do a lot of calculations, and that goes way past anything we're going to do in this class. So in general, if you're given the slant height and you're given the dimensions of the base, you can calculate the surface area just using this formula, d squared plus 2dl. You're not going to have to worry about it much beyond the actual measurements. Now, as long as we're in this neighborhood, we notice that if we know the area of the base of a pyramid and its height, the volume of a pyramid is 1/3 area of the base times the height. And so for that pyramid we had before, so a pyramid with 36 square meter base and a height of 4, has volume equal to 1/3 36 square meters times 4 meters, winds up being 12 times 4 is 48 cubic meters.